Hello everybody and welcome to example 1 on page 23 of the workbook. Let's take a minute to read this example together. They would like us to calculate a formula for f prime of x if f of x is equal to x squared minus 2. Notice that we're given a graph of that function to the right. X squared minus 2 is just a parabola. And after we do that, they'd like us to sketch a graph of the derivative on the diagram. Okay, so f prime of x, we have a formula for that. We've been calculating the derivative as a limit. So it looks like the limit as h goes to 0. And normally what we have is the limit as h goes to 0 of f of a plus h minus f of a over h. Okay, here we're thinking of the a as being a variable. We're talking about an entire function, so that formula will turn into the limit of f of x plus h minus f of x over h. It's like we're substituting the x for the a. Okay, now we've got some algebra to do here. Okay, so we're taking the limit as h goes to 0. First thing we need to calculate is f of x plus h. So we're thinking of x plus h as being our input. We're going to go to our formula for the function and plug in an x plus h everywhere that we see an x. Okay, so we'll get x plus h squared minus 2. Okay, and then next thing we come to is f of x. And there we're just going to plug in x for itself, and so the function is going to look the same. All of that's divided by h. Okay, we just need to do the algebra and see what we get. Okay, so let's see. Starting with the x plus h squared, if we FOIL that out, we're going to get x squared plus 2xh plus h squared minus 2. Then we could take this minus sign and distribute it through. And that's going to give us a minus x squared plus 2. All right, and we've got an h in the denominator of our fraction, so we can't directly plug in h equals 0, which means we're going to need to do some algebra and hopefully simplify this. So a couple of nice things happen here. Notice that there's a minus 2 and a 2. Those cancel. And then there's an x squared and a minus x squared. Those also cancel. And we are left with the limit as h goes to 0 of, let's see, 2xh plus h squared over h. Do you notice any more simplification we can do there? Okay, there's an h that we can factor out in the top. So if we pull an h out, we'll have a 2x plus h left over. And factoring that h out is a nice thing to do because we get cancellation now. Those two h's cancel in the top and the bottom. And now we can let h go to 0, which means substituting h equals 0 into our expression here, we're just going to get 2x plus 0 out of this. Okay, which is 2x. Okay, so what we have shown then is that the derivative function of x squared minus 2 looks like 2x. So let's put that into words here. Okay, we could ask the question, what is that the graph of? If you drew the graph of y equals 2x, what would you get? Well, that's just a line with a slope of 2 and a vertical intercept of 0. Okay, and y-intercept 0. Okay, so to graph the derivative function, we just need to graph a line whose slope is 0 and whose slope is 2 and whose y-intercept is 0. Okay, so we'll start with the y-intercept of 0, and a slope of 2 means that we're going to go up 2 and over 1. Notice the scale. There's 2 and there's 1. Okay, and so we get a point there, and if you got a few other points, you would notice that they all lie along this line that I'm drawing. Okay, and that line is the derivative function that we just calculated. Okay, now we're technically done with the problem here, but I'd like to go a little bit deeper here just so we can see some of the connections between this derivative function and what information it's really telling us. Remember that those words that we mentioned in the preliminary example, that the slope of f, the original function, equals the y values of the derivative, or I should say y value, I guess. So for example, if we went to, I'm just going to pick a point on the derivative graph, maybe here. Okay, what's the y value at that point? Well, that looks to be 3. So that y value has to match the slope of the original function, which means that if we find the same corresponding point on f, the slope of the tangent line there should be 3. Okay, that slope has to match the y-coordinate of the derivative. And you should be able to do that in theory for any point, any other point on the derivative graph. Let's just pick another one, maybe here. What's the y-coordinate there? Well, it's -3, and that means that if we find the corresponding point on the function and draw the tangent line, the slope should match the y-coordinate of -3. Okay, and you could do that experiment for every single point on the entire graph of the function that we have here.